This video is on the objective complete the steps of a two-mean hypothesis test, but this is with dependent samples. So remember, when the samples are dependent, it really turns into a one mean hypothesis test where you're looking at the mean of the differences in the values in these dependent samples. You'll see in a second. And this is using the critical value approach. Right? So we're going to find a critical value or critical values depending on what kind of a test it is, and setting up rejection regions and all that. Alright. So again, if you want to see more about what they're saying on this, click on More Instruction. Look at their videos, their notes, their examples. Hopefully those help you out. Alright, so here, a concrete manufacturer wanted to test the durability of two different types of reinforcements to its concrete, rebar and fiber. Employees who work in the research and development department cast 6 different sizes of concrete, making one of each size with rebar and one of each size with fiber. Then, the employees put the concrete under a steadily increasing amount of stress and measured the time it took for the stress cracks to first appear in each type of concrete. So the results in minutes are shown in the following table. Right? So again, these are paired data. Right? In fact, I'm going to start writing this stuff out on some paper here. Right? We have our paired data, where that first piece of concrete or the first type of concrete, I should say. As they say, they cast 6 different sizes of concrete. So first size, first type. Well, the first type of concrete, one's made with the rebar to reinforce it, one's made with fiber. And this first type, when they put it under so much a certain amount of stress, it takes 15 minutes to crack when it's made with rebar. Only takes 9 minutes to crack when it's made with fiber. And then the second type of concrete, the second size, under that stress, some stress takes 16 minutes to crack when made with rebar, 14 minutes to crack when made with fiber. All right, then you got the third type, the fourth type, the fifth type, and the sixth type. All right, the third type, 18 minutes to crack when it's made with rebar, 10 minutes to crack when it's made with fiber. The fourth type, 19 minutes when made with rebar, 16 minutes when made with fiber. And the fifth type, 20 and 21. And the sixth type, 11 and 13. Okay. All right. Now, they're going to say, assume that both of the populations, are normally distributed. So that way it doesn't matter that the size of the sample is small, right? There's only these 6 different sizes of concrete. We'll still be working with a t distribution here with 5 degrees of freedom, because there are going to be 6 differences. At the 0.01 level of significance, right, alpha, is there sufficient evidence to show that there is a change in the average amount of time until stress cracks appear between rebar and fiber? All right, so this is the claim here that's being tested, the statement being tested. Just that there is a change in the average amount of time it takes for stress cracks to appear. So what we're going to do is look at the difference in the amount of time, right? And they're telling us to take the differences by taking the rebar times minus the fiber times, right? So I'm going to go to my paper again and say, make a third column, right? Again, these are paired data, right? Because again, these two values have to be next to each other because they're related to that first type of concrete, right? These two values have to be next to each other because they're related to that second type, and so on. This is paired data, dependent samples. And when we were given the paired data, right, dependent samples like this, we looked at the sample of differences. And again, they told us to take the differences this way. Take the rebar times to crack minus the fiber times to crack. So 15 minus 9, right? 6 minutes difference. 16 minus 14, 2 minutes difference. 18 minus 10, 8 minutes difference. 19 minus 16, 3 minutes difference. 20 minus 21, negative 1, right? So again, that means that the fiber took longer to crack this time. All these, when it's positive, rebar takes longer to crack. When it's negative, that means the fiber, the one made with fiber, takes longer to crack. Then 11 minus 13, negative 2. And then we're going to focus on this sample of differences. All right, we're going to focus on this sample of differences. I want to find the sample mean, right, which is going to be called d bar, right, the average of these sample differences. And I also want to find the sample standard deviation, which is going to be called S sub d, right, around that whatever. And when we're working at this, when we're going through the test later, if I were to do this for all different groups of 6 types of concrete, 6 sizes of concrete, and look at all their d bars, the d bars would be would have a distribution that's a student's t distribution with n minus 1. Right, so 5 degrees of freedom. Right, there are 6 differences here. We'd be looking at a student's t distribution with 5 degrees of freedom. All right, so again, that's all coming later. This is going to come in handy later. But for right now, we're going to focus on setting up the hypotheses. Now, in order to do that, remember for these tests, when we're dealing with paired data, the claim and the hypotheses all have to do with this mu sub d. Mu sub d is the average difference in crack time, right, the time it takes for these to crack under stress for all types of concrete. Right. So this would be the average difference in cracking time, I'll say, for all, right, for the population of concretes, for all types of concrete or all sizes of concrete, whatever they said. All right. So the claim being tested, right, the claim being tested here, right, they said they want to show, is there evidence to show that there is a change in the average amount of time until stress cracks appear between rebar and fiber? Just saying that there is a change doesn't mean that one is greater than the other, or the other one's rebar is greater than fiber, or rebar is less than fiber. It's just that there is a change. They're not the same, so that their difference isn't 0 on average. Right? So the claim here is that mu d is not 0. All right. Another way to say that in words is that, the difference, there is a difference on average in this cracking time under stress. There is a difference on average, right, in these cracking times. And then once a claim is established, you have the null hypothesis, the alternative hypothesis. Now this does not involve equals, this claim, this statement being tested, so that's going to be represented by the alternative hypothesis. And then the null hypothesis is always the opposite of this, which would be just as, mu d equals 0. And this is what we're going to be assuming. We're going to assume that there is no difference. Right, that mu d equals 0. That means that on average, there is no difference in the cracking time for the concrete made with rebar and the concrete made with fiber. All right. So we're going to assume this, and then go through, use our sample data here to test this. All right. So, and then from this alternative hypothesis, also you can say what kind of a test it is. Right. This would be a two-tailed test. Right, because this is a parameter is not equal to some value. All right, so let's put this stuff in first. That's what they're asking us first. So the null hypothesis, we're going to assume that there is no difference on average between the cracking times, that mu d equals 0. And then the alternative hypothesis is just that there is a difference, there is a change in these average cracking times, right? So that mu d is not equal to 0, a two-tailed test. Now, if they said something about rebar time being greater than fiber time, then it would be a right-tailed test, or rebar time being less than fiber time, cracking time would be a left-tailed test. But it just said that there was a change, there was a difference. Okay, so that's just step one. I mean, we're going to go through all the steps of a hypothesis test here. All right, so now we're asked to find the test statistic, right? Remember, this is a t-score. We're working with a t-distribution with 5 degrees of freedom. And I've written this out in previous videos, right? We're working with this t-distribution with 5 degrees of freedom. This is our sample of differences here. The test statistic is a t-score. And we're going to take the average of all these differences. We're going to take the d bar and subtract it from the mean of the population of all the differences. But remember, this was assumed to be 0 from the null hypothesis. So really, I just have d bar in the numerator divided by, and then the standard deviation of the distribution of d bars, which would, since students t would be the standard deviation of the sample. Right, the standard deviation of this sample of 6 differences divided by the square root of the sample size divided by the square root of 6. So I need to find, like I said earlier, I need to find the mean and the standard deviation of these 6 differences, right, with the rebar minus fiber. So I'm just going to have the calculator. I'm going to do that on a calculator. All right, I'm just going to put that in as a list. So stat, edit. Now, I'm hoping you've seen other videos of mine where you can enter the rebar list, like say that as list 1, enter the fiber list as list 2, and then go to list 3 and just have it be list 1 minus list 2, and you'll get list 3 as all these differences. So that'd be quicker for like other problems, but I've already written all the differences down, so I'm just going to have L1 be my differences. So 6, 2, 8 minutes, 3 minutes, -1 minutes, and -2 minutes. So I'm just going to enter all these down list 1 since I already took them by hand. And then I go stat, calc, one variable stats, because I only got this one list of data here. And, I had L1, right? List L1 was my list of differences. No frequency list, calculate. And the average is 2 2/3. All right, this d bar. Oh, you know what? I didn't have the calculator up. I am so sorry. So I went stat, edit, and I just put these values down list L1. I'm sorry, I forgot to put that up. But like I said earlier, you could put the rebar times down L1, the fiber times down L2, and then have L3 be equal to L1 minus L2, and it'll pop out all these 6 differences, all right? And then I got out of there and I went to stat, calc, one variable stats, list L1 had my differences in it, and then calculate. All right, so the X bar, which is the D bar, the average of this sample, is 2 2/3. All right, so 8/3, or approximately 66666. So let's say 667. All right. And then the standard deviation is this SX line. Don't use sigma. All right, we only know the standard deviation. This is a sample. So 3.88158, approximately 3.882. Right, if I go to 3 decimal places or whatever. All right, so I'm going to use these values in my test statistic calculation. All right. So the test statistic for our d bar, right, for this sample is, I'll go 2.667, right, the average of the sample, the average of those differences, divided by, and then the standard deviation was about 3.882, divided by the square root of 6, right? There were 6 values in that sample. Let's see what I get. Now, you can enter these values here. I'm going to show you that you can just use these values that came up. Now, if you use the rounded values, you're going to get something. Let me show you the, if I just go 2.667 like I did here with the rounded mean divided by, and then 3.882 divided by the square root of 6. I use the rounded standard deviation. Oops. And do all that. See, I'm getting about 1 point. Now they say round to the nearest hundredth, so about 1.68 for the t-score. Now, if you want to be more accurate, you can do this. For this d bar, go variables, hit number 5. See statistics at number 5. Hit number 5, and then see number 2 is x bar. That's the mean divided by, and then in parentheses. And then the standard deviation, hit that variables button again, go to number 5, and then use this SX, and then divide that by the square root of 6. Right. And this will be a little more accurate. Right, this should be a little more accurate. So, now, they both round to 1.68 though, so that's nice. Didn't throw anything off too much by rounding. So yeah, 1.68 is the t-score, the test statistic for my sample. All right, so I'm going to go back here, enter that, 1.68. Wonderful, and again, they show you the same kind of calculations I just showed you. All right. Yeah, they use the rounded to 3 decimal places. See, they use the rounded, but still, I got 1.68 either way. All right, then I'm sure they're going to have us find the critical value or critical values now, because it is a two-tailed test. Right? So yeah, see, find the critical values for t. So again, back to my paper. So remember, the distribution of my d bars is a t distribution, student's t distribution, with 5 degrees of freedom. All right, so I'll draw that. All right, I'll draw that here. Yeah, so here's a number line representing possible t-scores. Bell shape, symmetrical. Underneath the peak is a t-score of 0. The significance level, I forgot to mention this earlier, right? The value of alpha was 0.01. And we said earlier it is a two-tailed test. Right? The alternative hypothesis was that there is a difference on average between the cracking times for rebar and fiber. So alpha is 0.01. Right, it's a two-tailed test, meaning I'm looking for 2 critical values, setting up 2 rejection regions, one in the right tail and one in the left tail, and these should be the same area. Right? Now I want the area of both of these together to be alpha, to be 1%. So that means I want the area over here to be 0.5%, 0.005. And I want the area of this left tail rejection region to also be 0.5%, right, 0.005. That way, the total area of the rejection regions is alpha. So this score I'm looking for is what's the t-score with an area of 0.005 or 0.5% above it, and this one is just the opposite of that, right, negative, and then the t-score with 0.005. Right? So I can find these either with a calculator, but I'll just show you how to use that table we're being provided. All right, so remember, degrees of freedom here was 5, 1 less than the sample size. There were 6 differences. So I go to this 5 row, and then I was looking for that t-score with 0.5% above it. So I'm looking at this last column with 0.005 here. So 5 degrees of freedom. That score is 4.032. So this value is 4.032, and then this other value is negative 4.032. And those are the critical values. Those are the entrances to my rejection region. And then what was our test statistic? The test statistic I just calculated was 1.68. Where does that fall? Well, that's definitely not in a rejection region. Right? There's the test statistic, 1.68. Not in a rejection region. All right, but we'll get to that in a second too. All right. So here, now let's see. It says, they're telling us here that sometimes they told us to separate them by commas if there was more than one. Here they're telling us if there are two of them, use the plus or minus sign. Right. So here, entering the critical values, I'll go the plus or minus, and then the 4.032 that I got from that table. Right. Wonderful. And again, they read through the answer explanations, getting the same, going looking at the same stuff I just showed you. All right, then I believe finally we're going to go through the step of, do I reject the null hypothesis or not? And then what kind of conclusion can I make? Right. So then, yeah. So going back to my paper. So again, because the test statistic is not in one of these rejection regions, I am not rejecting the null hypothesis, right? We fail to reject the null hypothesis. So if you look at your hypotheses, right, here were the hypotheses. We're keeping this, then. We're not rejecting it. So this statement that, I'm assuming this statement that there is no difference on average between rebar cracking times and fiber cracking times, I'm keeping that. We're going to keep that. And if we're not rejecting this, that means we are rejecting or not supporting the alternate. And that was the claim, that there was a difference between the times on average. We're not supporting that. We're not saying that. All right. So back here, again, we're not, it's going to be one of these where it says fail to reject. But then I got to look at the explanation. I got to look at the conclusion. So this says fail to reject the null. There is enough evidence or sufficient evidence to show that there is a change in the average amount? No. We're saying I didn't want to say that. Right? That was the claim. I'm not supporting the claim. So it's this other one, right? Fail to reject. There is not sufficient evidence to show that there is a change in average amount of time until stress cracks appear between rebar and fiber. That was what I wanted to say. That's what I said out loud a second ago, where we're not supporting the claim. Okay? Wonderful. So again, a lot of stuff, but you've seen this over and over again now. You've seen several types of hypothesis testing, and it's the same steps every time with this, and this is the critical value approach. You have a claim, being made about some parameter. Here it's that mu d. Then you set up your hypotheses, right? Your null hypothesis always involves equality. Your alternative hypothesis doesn't. You take some samples, you use that sample information to, first you should state your significance level alpha, and then you take samples and use the sample information to find a test statistic. In this case, it's a t-score. Then you find your critical values, set up rejection regions, make a decision. Do I reject the null hypothesis or not? And then make a conclusion, right? The critical value approach is the same every single time, right? It's just the scenarios change, that's all. What we're doing is different, but the steps are the same. All right, and hopefully watching me go through this, looking at your more instruction if you need to, reading the answer explanations when they come up. I'm hoping all this stuff helps you out when you're working on this material on your own. And thank you very much for watching.